In this study, the interpretation of finite fracture mechanics is proposed based on the criticality of the damage-failure transition attributed to the specific metastability of free energy release. Multiscale mechanisms of fatigue damage-failure transition in metals are studied for very high cycle fatigue and are analyzed as a duality of inertiality-linked singularities, collective modes of defects, and stress field singularity within the classical framework of fracture mechanism. Special structure scales corresponding to different stages of the damage-failure transition are identified through the analysis of roughness correlation and estimation of the power exponent, and corresponding structural lengths of characteristic fracture surface areas. These lengths and power exponents are utilized in the constitutive laws as structure-sensitive parameters for the characteristic stage of the damage-failure transition, including small cracks initiation and growth and the Paris crack advance. Fatigue symmetric tension compression test at 20 kHz was conducted on an ultrasonic fatigue testing machine for the R5 high-strength steel specimens with the purpose to establish damage-induced scattering properties in the process zone. 3D new view image roughness data revealed the existence of two characteristic scales, the scale of process zone and correlation length. That is a scale when correlation behavior of defects-induced roughness has started. The values of critical distance under fatigue loading of the R5 steels correspond to the value of L process zone, and the Paris crack threshold stress intensity factor are shown in this slide. High frequency condition of very high cycle fatigue loading provides the unique opportunity to study of the role of different factors and the mechanism of damage localization and crack advance. Qualitative difference of small crack and the Paris crack advance is reflected to the values of power exponents and corresponding leading mechanism responsibility for damage localization at the process zone area.